Hello there and welcome to the Streamberg Space Stories. I'm glad you found your way here tonight. Maybe you're lying in the dark right now, or maybe you've got the lights turned low and the world outside has gone quiet. Either way, I'm glad you're here. Tonight, we're going somewhere we have not been before. Not to a distant galaxy, not to the surface of a star. Tonight, we're going to think about something that has not happened yet. Something that might never happen, and something that, if it does, could quietly change everything we understand about being alive. Before we begin, if these calm explorations of science help you drift off, or simply give you something thoughtful to carry into the night, feel free to like and subscribe. It really does help others find their way here too. Drop a comment if you feel like it. Now settle in, let your breathing slow. You do not need to do anything at all, just listen. Imagine for a moment that a small capsule falls from the sky. It has been falling for a very long time, not just from the upper atmosphere, the way a satellite drops, but from much further away, from another world entirely. It has travelled across tens of millions of miles of darkness and silence, wrapped in heat shields and ceramic plating, carrying inside it a handful of dust and rock collected from a place no human hand has ever touched. The capsule drifts beneath its parachute and lands in a flat stretch of desert, somewhere dry and empty and far from anything. A team of scientists in orange suits rushes toward it. They have trained for this moment for years, decades, some of them. They know exactly what they are doing, they know how to handle it, how to transport it, how to keep it sealed. They know how to protect it from the wind, the moisture, the bacteria of Earth, and they move quickly, not because the capsule is fragile, but because every second it spends in the open air is a second in which something could be exchanged. Something invisible, something unmeasured. But here is the question that hangs quietly behind everything they do. The question no one says aloud but everyone carries, like a weight behind their ribs. What if there is something alive inside? Not alive the way you or I are alive, not a creature with eyes or legs or intention, but something ancient, something microscopic, something that has been sleeping in that rock for 1 billion years and is now, for the first time, being brought into the warmth and wetness and oxygen of our world. Something we cannot see, something we do not know how to test for, something that does not play by any of the biological rules we have ever written. What then? That is what tonight is about. Not a horror story, not a doomsday prophecy, just a quiet, careful question about what happens when we reach into the unknown and bring something back. Because we are doing that right now, and the answer, honest and true, is that we do not entirely know. Human beings have always been collectors. Long before we were scientists, we were gatherers. We picked up stones and shells and bones and carried them home, turned them over in our hands, held them up to the light. We built our understanding of the world by taking pieces of it and studying them closely. So perhaps it was inevitable that once we learned how to leave our planet, we would want to bring pieces of other worlds home too. The first time we did this was in July of 1969. The Apollo 11 crew, Armstrong, Aldrin and Collins, returned from the moon with just over 21 kilograms of lunar rock and soil packed into sealed containers. They were the first humans to walk on another world, and they brought its dust back with them. It was an extraordinary triumph, but even in that moment of celebration, there was a quiet, nervous undercurrent running through the scientific community. Nobody truly believed the moon harboured life. It had no atmosphere, no liquid water, no protection from the sun's radiation. The surface baked at over 100 degrees Celsius in the lunar day, and plunged to below -170 at night. It was, by every measure, a dead place. And yet, NASA could not be entirely certain. The history of science is, after all, a long and humbling record of things we were certain about, until the moment we were proven wrong. Just 2 months before launch, Michael Crichton had published The Andromeda Strain, a novel about a lethal alien microbe arriving on Earth aboard a satellite. The book became a bestseller almost immediately, and the public imagination was primed for exactly the kind of fear that the space agency could not afford to dismiss. So they quarantined the astronauts. For 21 days after splashdown, Armstrong, Aldrin and Collins were confined first inside a converted Airstream trailer on the deck of the USS Hornet, and then inside the Lunar Receiving Laboratory at the Manned Spacecraft Center in Houston. They wore biological isolation garments. Their air was filtered. 24 support staff were sealed in with them. Scientists introduced lunar material to mice, fish, quail, cockroaches, shrimp, and various plants, watching for any sign of illness or abnormality. None came. The moon was, as expected, lifeless. The quarantine was lifted, and after 2 more missions repeated the process with similarly uneventful results, NASA dropped the protocol altogether by Apollo 15. The danger had never materialized, and it seemed in hindsight almost quaint to have worried. But there is a detail about the Apollo quarantine that is less often told. Years later, a careful review by the National Research Council concluded that the quarantine had been, in their words, a failure. Not because anything harmful was found, but because the containment was never truly airtight. There were breaches, seals that did not hold, moments where lunar material was briefly exposed to the open air. If something dangerous had stood inside those rocks, it would very likely have escaped before anyone could have stopped it. The program had been built in a rush, under enormous political pressure, and planetary protection had in practice been overruled by operational expediency. We were lucky. The moon really was sterile. But the lesson is worth remembering, because the places we're reaching for now are nothing like the moon. And there is another lesson too, one that is perhaps more subtle. The Apollo quarantine failed not because the science was wrong, but because the politics were stronger. The Cold War demanded speed. National prestige demanded results. The biological containment program was staffed by dedicated people, but it was underfunded, rushed, and ultimately subordinated to the larger imperative of beating the Soviet Union to the lunar surface. Many of the scientists working in the Lunar Receiving Laboratory, particularly the physical scientists, were openly skeptical that quarantine was necessary at all. They knew from first principles that the moon was lifeless, and they saw the containment protocols as an inconvenience. The result was a culture in which corners were cut and breaches went unreported. It is a pattern that echoes through the history of risk management. When the probability of danger is perceived to be low, the discipline of preparedness erodes, and it erodes fastest precisely when it is most needed. In the decades since Apollo, we've continued to bring pieces of other worlds home, though much more carefully and from much further away. In 2004, NASA's Stardust mission returned particles captured from the tail of Comet Wild 2, tiny grains of interstellar dust that had been drifting through the solar system since before the planets formed. In 2010, Japan's Hayabusa spacecraft delivered a tiny quantity of dust from the asteroid Itokawa after a journey marked by engine failures, communication blackouts, and a landing that went so wrong it nearly ended the mission entirely. The spacecraft bounced off the asteroid's surface, failed to fire its sample collection projectile, and limped home on a single functioning ion engine. When engineers opened the capsule, they found only about 1,500 microscopic grains. But those grains were enough. They were the first samples ever returned from the surface of an asteroid, and they changed our understanding of how these small bodies age and erode in space. Hayabusa's successor was far more ambitious. Hayabusa 2 launched in 2014 and reached the carbon-rich asteroid Ryugu 4 years later. It deployed rovers that hopped across the surface in the low gravity, fired a copper projectile to blast open an artificial crater, and collected samples from both the surface and the subsurface. In December of 2020, the spacecraft released its sample capsule over the Australian outback, where it was recovered in pristine condition. Inside were just over 5 grams of dark carbon-rich gravel. Analysis revealed that the material contained amino acids, the fundamental building blocks of proteins, along with organic compounds that predated the formation of the solar system itself. Ryugu's chemistry was a snapshot of the ingredients that were available when the planets coalesced from their primordial disk of gas and dust, 4.5 billion years ago. And then, in September of 2023, something truly remarkable happened. NASA's OSIRIS-REx spacecraft, after a 7-year journey spanning more than 7 billion kilometers, released a capsule that parachuted into the Utah desert, carrying roughly 250 grams of rock and dust from the asteroid Bennu. It was the largest asteroid sample ever returned to Earth. The material was whisked away to a specially built curation laboratory at the Johnson Space Center in Houston, where it was opened inside nitrogen-filled glove boxes to prevent any contamination from Earth's atmosphere. What scientists found inside was extraordinary. The Bennu samples contained water molecules trapped in mineral crystals, amino acids, nucleobases, and sugars essential for biology. In 2025, researchers announced the sample held many of the fundamental building blocks of life. Not life itself, but the raw ingredients from which life, as we understand it, could begin. None of these missions posed a serious biological risk. Asteroids and comets, while rich in organic chemistry, are not considered likely habitats for living organisms. The temperatures are too extreme, the radiation too intense, the liquid water non-existent. The planetary protection requirements for these missions were accordingly modest. The samples needed to be kept pristine for scientific purposes, but there was no real concern about something dangerous hitchhiking home. Mars is a different story entirely. For as long as we have known Mars as a world rather than a wandering light, we have wondered whether it might hold life. The earliest telescopic observers thought they saw canals and vegetation. The first close-up photographs from the Mariner missions in the 1960s revealed a barren, cratered surface that seemed to put those fantasies to rest. But then came the orbiters, then the landers, then the rovers, and with each new mission, the picture grew more complicated. In 1976, NASA's 2 Viking landers became the first spacecraft to operate successfully on the Martian surface. Their primary mission was to search for life. Each lander carried a biology package containing 3 experiments designed to detect metabolic activity in the soil. One of them, the labeled release experiment, produced results that initially looked positive. Martian soil appeared to react with nutrients in a way that mimicked what living organisms would do. For a brief, electric moment, it seemed possible that life had been found. But the other 2 experiments showed no sign of organic chemistry, and most scientists eventually concluded that the results were caused by highly reactive chemicals in the soil, not biology. It was a lesson in how difficult it is to design experiments that can distinguish life from chemistry when you're working on another planet with instruments that cannot be adjusted or repaired. Mars, it turned out, had not always been the cold, dry, irradiated desert it is today. Billions of years ago, rivers carved valleys across its surface. Lakes filled its craters. A thicker atmosphere kept the planet warmer, and liquid water flowed freely. The evidence is written in the geology. Deltas where rivers deposited sediment, mineral deposits that can only form in the presence of water, clay beds that suggest long periods of standing liquid on the surface. Mars was not always the forbidding place it is today. For a time, perhaps as long as 1 billion years, it may have been as hospitable to microbial life as the early Earth was. The two planets formed at roughly the same time, from roughly the same materials, in roughly the same region of the solar system. If life emerged on Earth during those early, chaotic, water-rich centuries, there is no obvious reason it could not have done so on Mars as well. And if life did arise there during that warmer, wetter epoch, the question becomes not only whether it existed, but whether traces of it might still be found, locked away in ancient rock, waiting for someone to come along and pick it up. Or, more provocatively, whether it might still persist somewhere beneath the surface, in aquifers or caverns shielded from the radiation that sterilizes everything exposed to the open sky. That is precisely what NASA's Perseverance rover has been doing since it landed in Jezero crater in February of 2021. Jezero is an ancient lake bed, fed by a river delta that carried sediment and water into the crater billions of years ago. It is, in the view of planetary scientists, one of the best places on Mars to look for evidence of past life. Perseverance has been systematically collecting rock cores, sealing them in sample tubes, and storing them either aboard the rover or depositing them at a designated collection point on the surface. And in July of 2024, Perseverance found something that made the scientific community pause. While exploring a set of rocky outcrops called the Bright Angel Formation along the edges of an ancient river valley, the rover came upon a peculiar rock. It was shaped like an arrowhead, about 1 meter across, and it was covered in strange markings, small dark flecks like poppy seeds, white ringed spots the scientist began calling leopard spots. The rock was named Cheyava Falls, after a waterfall in the Grand Canyon. When Perseverance's instruments analysed the rock, they found organic carbon, phosphorus and sulfur, along with 2 iron-rich minerals called vivianite and greigite, arranged in patterns that, on Earth, are most commonly associated with microbial metabolisms. The chemistry pointed to low-temperature reactions in a watery environment, exactly the kind of setting where microbes could thrive. In September of 2025, after more than a year of analysis and peer review, NASA published the findings in the journal Nature and described the Cheyava Falls sample as the mission's strongest candidate for a potential biosignature. Not confirmation of life, they were careful to say, not proof. But the closest thing we've ever found to evidence that Mars may once have been home to living organisms. The sample is now sealed inside a tube, stored aboard the rover, waiting to be brought home. And bringing it home is where the story gets complicated. For decades, the Mars Sample Return mission has been the single most desired objective in planetary science. Rover instruments can tell us a great deal, but there are experiments that can only be performed in terrestrial laboratories with equipment too large, too sensitive, or too power-hungry to send to another planet. To truly determine whether the patterns in Cheyava Falls were made by biology or by some unknown abiotic chemistry, scientists need to hold that rock in their hands. But Mars Sample Return has also been one of the most troubled missions in NASA's history. The original plan, developed jointly with the European Space Agency, envisioned a lander, a small rocket to launch the samples into Martian orbit, a European orbiter to catch the capsule and bring it to Earth, and possibly helicopters to help retrieve sample tubes from the surface. The projected cost ballooned past $11 billion. Timelines slipped. Reviews found the plan technically fragile and financially unsustainable. In 2024, NASA scrapped the original architecture and turned to industry for cheaper alternatives. Multiple redesigns followed. The mission was simplified: a smaller rocket, a lander based on proven technology, a different approach to breaking the chain of contact between Mars and Earth. But in May of 2025, the presidential budget proposal called for cancelling the program entirely. In January of 2026, Congress effectively confirmed that decision by eliminating nearly all future funding. The samples Perseverance has collected, including the one from Cheyava Falls, remain on Mars. As of tonight, there is no approved mission to retrieve them. Meanwhile, China is pressing forward with its own plans. The Tianwen-3 mission, expected to launch around 2028, aims to land on Mars, collect samples using surface scoops, a 2-meter drill, and even a small drone, and return them to Earth by approximately 2031. If it succeeds, China will become the first nation to bring Martian material home, and whoever does it first will face the same fundamental question. What do you do with a tube of Martian dust that might just possibly contain something alive? To understand why this question matters, you have to understand what life on Earth has taught us about the limits of survival. Because life, as it turns out, is far more tenacious than we ever imagined. Over the past few decades, a revolution has taken place in microbiology, one that has not received nearly enough public attention. We have discovered that the biosphere does not end at the surface. It extends deep into the Earth's crust, into environments that were, until recently, thought to be as sterile as the Moon. Deep beneath the ocean floor, in places where no sunlight has reached for millions of years, bacteria thrive in cracks in the rock, drawing energy not from the sun but from chemical reactions between water and minerals. They are called chemolithotrophs, organisms that eat stone, and they live at temperatures and pressures that would destroy almost any organism we encounter in daily life. Some have been found more than 3 kilometers below the seabed, in sediments that were deposited tens of millions of years ago. Their metabolisms are so slow that a single cell division might take centuries. They exist in a state of biological patience that defies our ordinary understanding of what it means to be alive. In the gold mines of South Africa, more than 2 kilometers underground, scientists have found communities of bacteria living in water that has been isolated from the surface for tens of millions of years. These organisms derive their energy from the radioactive decay of uranium in the surrounding rock, which splits water molecules and produces hydrogen, which the bacteria then metabolize. They are in effect nuclear-powered life forms, sustained not by the sun or by organic matter, but by the slow disintegration of heavy elements. Their discovery forced a profound revision of what we consider habitable. If life can persist in the deep Earth, drawing energy from radioactivity and mineral chemistry, then similar conditions might exist on other worlds. In the hyper-arid core of the Atacama Desert, often used as a stand-in for Martian conditions, microbes persist in salt crystals and within the pore spaces of rocks, extracting the barest traces of moisture from the atmosphere. At the bottom of Antarctic ice sheets, in lakes sealed off from the surface for hundreds of thousands of years, bacterial communities have been found living in liquid water kept from freezing by pressure and geothermal heat. In the cooling pools of nuclear reactors, a bacterium called Deinococcus radiodurans survives radiation doses thousands of times greater than what would kill a human, repairing its own shattered DNA with a speed and efficiency that borders on the miraculous. It carries up to 10 redundant copies of its genome, giving it the raw material to reconstruct itself even after catastrophic damage. And then there are the tardigrades. These microscopic animals, barely 0.5 millimeter long, with 8 stubby legs and a lumbering gait that earned them the name water bears, are among the most resilient creatures ever discovered. When conditions become hostile, tardigrades enter a state called cryptobiosis. They expel nearly all the water from their bodies, retract their limbs, and curl into a tiny desiccated ball called a ton. In this state, their metabolism drops to less than 0.01% of normal. They are, by most meaningful biological definitions, not alive, but they are not dead either. In the ton state, tardigrades have survived temperatures close to absolute zero and well above the boiling point of water. They have endured pressures 6 times greater than those found in the deepest ocean trenches. They have tolerated doses of radiation that would sterilize a hospital. And in 2007, they became the first animals to survive direct exposure to the vacuum of space. During the European Space Agency's Photon M3 mission, dehydrated tardigrades were placed on the exterior of a satellite and exposed to the hard vacuum and cosmic radiation of low Earth orbit for 10 days. When they were brought back and rehydrated, many of them revived. Some even went on to reproduce. A protein in their cells called DSUP, short for damage suppressor, shields their DNA from radiation in ways we're only beginning to understand. In 2016, scientists inserted the DSUP gene into human cells in a laboratory and found that those cells became significantly more resistant to X-ray radiation. The tardigrade survival toolkit is, in a very real sense, a biological technology that evolution spent hundreds of millions of years perfecting. In 2019, thousands of tardigrades in their cryptobiotic state were aboard the Israeli lunar lander Bereshit when it crashed into the surface of the moon. Scientists debated whether any of them could have survived the impact. The consensus was that the shock pressures were likely too great, but the possibility could not be entirely ruled out, and that uncertainty is itself a kind of lesson. In 2020, a Japanese research team led by Akihiko Yamagishi at the Tokyo University of Pharmacy and Life Sciences published results from an experiment that had been running on the outside of the International Space Station for 3 years. Pellets of the bacterium Deinococcus radiodurans, arranged in layers of varying thickness, had been exposed to the full intensity of space, unshielded by any rock or container. The outer cells died, as expected. But the inner cells, protected by the dead outer layer, survived. 3 years, fully exposed in space. It was a finding that hinted at something remarkable. Microorganisms might be able to travel between planets not inside meteorites, as had previously been theorized, but simply in clumps of cells drifting through the void. The point of all this is not that Martian life is likely. It is that life, once it takes hold, is extraordinarily difficult to kill. And if it ever did take hold on Mars, during those warmer, wetter billions of years, it may have evolved its own survival strategies. Strategies we cannot predict, because they would have been shaped by a world with different chemistry, different pressures, different radiation. We would be encountering a biology written in a language we have never read. This brings us to perhaps the most unsettling question of all. If Martian microbes do exist, and if they were brought to Earth, could they actually do anything? Could they infect us? Could they disrupt our ecosystems? Could they interact with terrestrial biology in a meaningful way? The honest answer is that nobody knows. There are arguments on both sides, and the scientific community is genuinely divided. Those who consider the risk negligible point out that Earth-based pathogens are exquisitely adapted to their hosts. Viruses, for example, work by hijacking the molecular machinery of specific cells, inserting their genetic material into the host's DNA using protein keys that fit very precise biological locks. A virus that evolved on Mars, assuming viruses could evolve there at all, would have no way of interfacing with the biochemistry of an Earth organism. It would be like trying to plug a Martian appliance into a terrestrial wall socket. The connections simply would not match. This argument is compelling, and for many scientists it is sufficient. The likelihood that an alien microbe could directly infect a human being or any other complex organism is, by most assessments, vanishingly small. But others urge caution. Anthony Riccardi, an invasion ecologist at McGill University, has pointed out that we do not even need to imagine infection in the traditional sense. On Earth, invasive species have devastated ecosystems not by causing disease, but by outcompeting native organisms for resources, or by disrupting chemical cycles that other species depend on. An alien microbe that could metabolize something abundant on Earth, something we take for granted as stable, could theoretically alter an environment in ways that ripple outward in unpredictable directions. It would not need to be pathogenic, it would only need to be different. There is also the possibility that Martian life, if it exists, might be so biochemically alien that our immune systems and our diagnostic tools would not recognize it at all. We might not even be able to detect it using standard biological assays. Most of our methods for identifying microorganisms rely on DNA sequencing, on culturing cells in specific media, on looking for molecular signatures we already know to look for. But what if Martian life does not use DNA? What if it uses a different information-carrying molecule altogether? We would be searching with a flashlight that only illuminates one color in a room that might be lit in wavelengths we've never seen. Some astrobiologists have even suggested the possibility of a shadow biosphere here on Earth, a population of microorganisms so biochemically different from the life we know that they have existed alongside us, undetected, because our instruments are not calibrated to find them. This idea remains speculative and unproven, but it illustrates a sobering point. Our ability to detect life is constrained by our understanding of what life looks like, and our understanding of what life looks like is based on a single example: life on Earth. We are working from a sample size of 1. Extrapolating from that to make confident predictions about what life might be or do on another planet is, at best, an exercise in educated guessing. This is not science fiction. This is a genuine gap in our preparedness that scientists working in planetary protection have been writing about for years. The problem is not that the risk is high. The problem is that the risk is unknown. And in science, unknown risks are the ones that deserve the most respect. The effort to manage this uncertainty has a name. It is called planetary protection, and it has been a formal discipline within space science since before the first satellite orbited the Earth. The concept was first discussed at the International Astronautical Federation Congress in Rome in 1956, a full year before Sputnik. Even then, scientists recognized that if we were going to send machines to other worlds, we needed to think carefully about what we might carry with us and what we might bring back. The concern was codified in the Outer Space Treaty of 1967, which was signed by more than 120 countries, including the United States and the Soviet Union, and which states that parties to the treaty shall conduct exploration of celestial bodies so as to avoid their harmful contamination and also adverse changes in the environment of the Earth, resulting from the introduction of extraterrestrial matter. From these words, an entire framework has been built. The Committee on Space Research, known as COSPAR, established a set of planetary protection categories that every space mission must follow. The categories range from 1 for missions with no significant concern through to 5, which applies to any mission that returns material from a body considered potentially habitable. Category 5 missions, such as a Mars sample return, carry the most stringent requirements. The samples must be contained at every stage of the journey. The chain of contact between the extraterrestrial environment and Earth's biosphere must be definitively broken, either by sterilizing the exterior of the return capsule or by sealing it so completely that no molecule can escape. When the capsule reaches Earth, the samples must be transported to a specially designed receiving facility and handled under protocols comparable to the highest biosafety levels used for the most dangerous known pathogens. Think about that for a moment. We build laboratories on Earth to handle Ebola, a virus we understand in considerable detail, and for which we have treatments and vaccines. For Martian material, we would need a facility that operates at that same level of containment, but for an agent we have never encountered, cannot describe, may not be able to detect, and have no idea how to treat. It is a containment challenge unlike anything in the history of biosafety. NASA, the European Space Agency, and the Japan Aerospace Exploration Agency have been collaborating on plans for exactly such a facility. The designs combine the cleanroom technology used to keep spacecraft free of terrestrial contamination with the biosafety protocols used in infectious disease laboratories. Scientists working inside would wear fully encapsulated suits with independent air supplies. Every surface would be sealed. Every exhaust vent would be filtered. The facility would be, in effect, a biological fortress, designed not to keep something out, but to keep something in. As of tonight, no such facility has been built. The plans exist. The engineering is understood. But construction depends on a mission that, at least on the American side, has been indefinitely deferred. There is one argument frequently made against worrying about back contamination at all, and it is worth examining carefully because it contains real scientific weight. Mars and Earth have been exchanging material for billions of years. When a large asteroid strikes Mars with enough force, it ejects fragments of Martian rock into space. Some of those fragments eventually cross the distance between the two planets and fall to Earth as meteorites. We have found more than 170 confirmed Martian meteorites in terrestrial collections. The transit time varies, but some are thought to have made the journey in as little as a few months. If life exists on Mars, the argument goes, then it has already arrived here, many times over, carried inside these natural projectiles. Earth's biosphere has been exposed to Martian material for aeons. If Martian microbes could survive the journey and interact with terrestrial life, they would have done so long ago. The fact that Earth's ecosystems appear unperturbed by whatever Mars has sent our way suggests that the risk is negligible. Some scientists, including the planetary scientist Robert Zubrin, have used this reasoning to argue that back contamination protocols are scientifically unjustified. Why spend billions on containment, the argument goes, when nature has already run the experiment for us? It is a provocative point, and it is not without merit. But the National Research Council examined this argument in detail and found it less reassuring than it first appears. The meteorites that reach Earth from Mars do not arrive gently. They are subjected to enormous shock pressures during the initial impact that ejects them, followed by years or centuries of exposure to cosmic radiation in space, followed by the searing heat of atmospheric entry. Each of these stages is likely to sterilize any organisms trapped inside, particularly near the surface of the rock. While it is theoretically possible for microbes deep within a large fragment to survive the journey, the probability decreases dramatically with each stage, and the total number of Martian meteorites that have reached Earth, while large in human terms, represents material from only a handful of original impacts over billions of years. A carefully collected, hermetically sealed sample returned by a spacecraft is a fundamentally different thing. It would be shielded from radiation during transit, protected from heating during re-entry, preserved in conditions designed specifically to keep any biological material intact. In other words, it would be the first time Martian material arrived on Earth in a condition optimized for life to survive the journey. That distinction matters. Mars is not the only world that troubles the planetary protection community. In some ways, it is not even the most concerning. In October of 2024, NASA launched the Europa Clipper spacecraft on a journey to Jupiter's moon Europa. It will arrive in April of 2030 and conduct 49 close flybys of the moon, studying its surface, its geology, and most importantly, the vast ocean that is believed to lie beneath its crust of ice. Europa is about the size of our own moon, but where our moon is dry and dead, Europa is thought to contain a global saltwater ocean that holds more than twice the volume of all Earth's oceans combined. The ice shell that covers it is estimated to be 10 to 25 kilometers thick, and beneath that shell, the ocean may be over 100 kilometers deep. It is kept liquid not by sunlight, which barely reaches this far from the sun, but by the tidal forces exerted on Europa by Jupiter's immense gravity, which flex and squeeze the moon's interior and generate enough heat to maintain liquid water. Where there is liquid water, there is the possibility of chemistry. Where there is chemistry, there is the possibility of life. And if hydrothermal vents exist on Europa's ocean floor, as many scientists believe they might, then Europa could host the same kind of energy-rich, mineral-laden environments where life is thought to have first emerged on Earth. Europa Clipper is not designed to detect life directly. It does not carry a microscope or a DNA sequencer, but it will analyze the composition of Europa's surface, measure the thickness of the ice, map the chemistry of any plumes that might be venting material from the ocean into space, and determine whether the moon possesses the conditions necessary for life as we know it. If the answer is yes, it will inevitably lead to calls for a follow-up mission, a lander, perhaps even a probe capable of melting through the ice and descending into the ocean below. And any such mission would face planetary protection challenges that make Mars look simple. Because Europa is not a world where life might have existed billions of years ago. Europa is a world where life might exist right now. Saturn's moon Enceladus presents a similar possibility, and in some ways an even more tantalizing one. Smaller than Europa, only about 500 kilometers across, roughly the distance from London to Edinburgh, Enceladus nonetheless harbours its own subsurface ocean beneath a shell of ice. And unlike Europa, Enceladus is not keeping its secrets entirely to itself. From great fractures near its south pole, the moon actively vents towering jets of water vapour and ice particles into space, plumes that rise hundreds of kilometres above the surface and feed material into one of Saturn's rings. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, flew directly through those plumes on multiple occasions. What its instruments found was remarkable. Water, salts, silica nanoparticles consistent with hydrothermal activity on the ocean floor, simple organic molecules, and molecular hydrogen, a potential energy source for microbial life. If you were to design, from scratch, a set of conditions suitable for life to emerge, you could scarcely do better than what Enceladus appears to offer: liquid water, chemical energy, organic building blocks, and mineral-rich hydrothermal vents. It is, in the view of many astrobiologists, the most promising place in the solar system to search for active, living biology beyond Earth. And there are others. Neptune's large moon Triton shows signs of geological activity that may indicate a subsurface ocean. Even Pluto, that distant, frozen world at the edge of the solar system, is thought by some to harbour a layer of liquid water beneath its icy surface. The more we look, the more we find that liquid water is not the rarity we once believed it to be. It is hidden away in oceans beneath ice, in aquifers beneath rock, in the dark places where sunlight never reaches but chemistry and heat persist. These ocean worlds represent a new frontier in astrobiology, and they raise a philosophical question that extends beyond the practical concerns of containment. If life does exist on Europa or Enceladus, it arose independently of Earth. It would be the second Genesis, a separate experiment in biology, conducted by the universe under different conditions, with potentially different chemistry, different structures, different rules. Encountering it would be, without exaggeration, one of the most significant events in the history of our species, and protecting it from us would be just as important as protecting ourselves from it. Within the scientific community, the debate over how seriously to take back contamination risks is neither simple nor settled. It is a conversation shaped by caution on one side and urgency on the other, and both sides have legitimate points. Those who advocate for aggressive exploration argue that the probability of finding dangerous organisms on Mars is astronomically low. Mars's surface is bombarded by ultraviolet radiation, baked by cosmic rays, and scoured by perchlorates, powerful oxidizing agents that are toxic to most known forms of life. If anything survives on Mars today, it is likely deep underground, in environments that Perseverance's surface sampling would never reach. The samples waiting on Mars are ancient rocks from a long-dead riverbed, not vials of active Martian biology. The precautions we take should be proportionate to the risk, they argue, and the risk is vanishingly small. Those who counsel patients make a different case. They point out that our understanding of what constitutes a biohazard is based entirely on Earth biology. We know what terrestrial pathogens look like. We know how they spread. We know how to test for them. But Martian biology, if it exists, would be the product of an entirely separate evolutionary history. We cannot assess what we cannot define, and until we have the tools and the facilities to safely analyze Martian material on Earth, bringing it home is an act of faith dressed up in the language of science. There is also a governance problem. The Outer Space Treaty assigns responsibility for planetary protection to the nations that launch missions, but it does not establish an independent regulatory body to enforce compliance. NASA has enormous expertise in this area, but it is a mission agency, not a regulatory one. As more countries and private companies gain the ability to send spacecraft to Mars and beyond, the question of who decides what level of precaution is sufficient becomes increasingly urgent. China's Tianwen-3 mission has stated that it will follow COSPAR guidelines and build a dedicated Mars sample laboratory with ultra-clean and biosafety areas. But the details of that facility and its containment standards have not been independently verified. We are entering an era in which the ability to bring material home from other worlds is no longer the exclusive domain of a single government agency With decades of planetary protection experience, it is becoming a capability shared by multiple nations and potentially by commercial entities. The rules that govern this activity were written in a different era, for a different scale of exploration. In 1969, just 2 months before Apollo 11 launched, Michael Crichton published a novel called The Andromeda Strain. It told the story of a deadly extraterrestrial microorganism that arrived on Earth aboard a military satellite and killed nearly everyone in a small town before scientists could contain it. The book became a bestseller. The film adaptation followed 2 years later, and the story seeded in the public imagination a very specific kind of fear. The alien plague, arriving from space, invisible and unstoppable. It is worth acknowledging that this fear has shaped the conversation about planetary protection in ways that are not always helpful. The scenario Crichton described, a hyper-lethal alien pathogen that kills on contact, is not what scientists are actually worried about. Real biological risks are subtler, slower, and harder to dramatize. They involve questions of ecology rather than epidemiology, of environmental disruption rather than individual infection. The Andromeda Strain made for a compelling thriller, but it is not a useful model for thinking about back contamination. What scientists are actually concerned about is something closer to what happens when an invasive species enters an ecosystem it was never part of. The introduction of rabbits to Australia, the zebra mussel in the Great Lakes, the chytrid fungus that has driven hundreds of amphibian species toward extinction, the brown tree snake in Guam, which wiped out nearly every native bird species on the island within a few decades of its accidental introduction. These organisms did not arrive with the intention to destroy. They simply arrived, and the systems they entered had no defenses against them, no evolved checks and balances. The damage was a side effect of novelty. There is a principle in ecology that the most dangerous invasive species are often those that exploit a resource or occupy a niche that nothing else in the new environment is using. They do not need to outcompete existing organisms head to head. They simply need to find an unoccupied space and fill it. And in the process, they can alter the environment in ways that cascade through the food web. If an alien microorganism could survive on Earth, and that is a very large if, the risk would not be that it attacks our bodies. The risk would be that it disrupts something we depend on, a soil chemistry, a water cycle, a microbial community that underpins an ecosystem we take for granted. It might be so slow that we would not notice for years. It might be so subtle that we would never trace it to its origin. And that is precisely what makes it difficult to prepare for. There is a concept in risk assessment called the unknown unknown. It refers to dangers we have not identified, not because we have failed to investigate them, but because we lack the framework to conceive of them. The known unknowns of Mars sample return are considerable. We do not know whether Martian life exists. We do not know what it would look like. We do not know how it would interact with terrestrial biology. But the unknown unknowns are, by definition, beyond our ability to enumerate. They are the questions we have not yet learned to ask. This is not a reason to stop exploring. Human beings have always ventured into the unknown, and the unknown has always carried risks. Every ship that sailed beyond the horizon, every expedition that entered an uncharted forest, every laboratory that cracked open a new phenomenon, did so without certainty about what lay ahead. Risk is not the enemy of discovery. It is its constant companion. And it is worth remembering that the greatest scientific discoveries have often come from moments of genuine uncertainty. When Antoine van Leeuwenhoek first looked through his handmade microscope in the 1670s and saw the teeming world of microorganisms in a drop of pond water, he had no framework for understanding what he was looking at. He called them animalcules, little animals, and the scientific establishment took decades to accept that this invisible world was real. When Alexander Fleming noticed in 1928 that a mould on his petri dishes was killing bacteria, he did not immediately understand that he had stumbled upon one of the most important medicines in history. Discovery often precedes understanding. We find things before we know what they mean. If we do find life beyond Earth, even the simplest microbial life, we will not immediately know what it means. We will not know its full chemistry, its full capabilities, its full implications. We will be in the position of Leeuwenhoek, staring through a lens at something we have never seen before, and our first task will not be to exploit it or to fear it, but simply to understand it. That understanding will take time. It will require patience, rigor, humility, and a willingness to say the three most important words in science: I don't know. But the scale of the stakes here is worth pausing to consider. When European sailors brought smallpox to the Americas, they did not understand germ theory. They did not know what they were carrying or what it would do. The devastation that followed was not the result of malice, but of ignorance, of a collision between two biological worlds that had evolved in isolation from each other. We are, in a very real sense, contemplating the same kind of collision, but this time we have the knowledge to be careful. We have the science to understand the risks, even if we cannot fully quantify them. We have the technology to build containment. We have the foresight to ask the question before the capsule lands. The question is whether we will use that foresight wisely. There is something deeply human about this tension. On one hand, the desire to know, to reach out, to touch something that has never been touched, to bring back proof that we were there, that we learned something, that the universe is not quite as empty as it sometimes seems. On the other hand, the caution that comes from understanding how fragile things are, how a single introduction, a single mistake, a single breach in containment can set in motion consequences that cannot be undone. Both impulses are valid, both are necessary. The history of science is a story of people who followed their curiosity into dangerous places and, more often than not, emerged with knowledge that made the world better. But it is also a story of people who underestimated what they were dealing with and paid a price that was not theirs alone to bear. Perhaps the truest measure of a civilization is not how far it can reach, but how wisely it can restrain itself, not out of fear, but out of respect. Respect for the unknown, respect for the complexity of systems we do not fully understand, respect for the possibility that the universe has made something we have not yet imagined, and that our first encounter with it should be conducted not with haste, but with care. The Perseverance rover is still working on Mars, collecting samples, analysing rocks, driving slowly across a landscape that was once a lake bed and is now a silent, rust-coloured desert. The tubes it has filled are waiting there, sealed and labelled, like messages in bottles that no one has come to collect. Inside one of them is a core from a rock that may, just possibly, contain the fossilised signature of something that once lived. 33 of its 43 sample tubes have now been filled. 8 contain igneous rock, 13 hold sedimentary material, 2 carry regolith, the loose soil of Mars, 1 holds a sealed sample of the Martian atmosphere, and 1, the one from Cheyava Falls, holds what may be the most consequential handful of dust ever gathered by a machine. Somewhere in Houston, a laboratory sits designed to receive samples that may never arrive. Somewhere in Beijing, engineers are building another. Somewhere in orbit, the Europa Clipper is falling toward Jupiter, carrying instruments that may, in a few years, tell us whether an ocean beneath the ice of a frozen moon holds the conditions for life. And somewhere tonight, in a place you cannot see, a child is looking up at the stars and wondering what is out there. That wondering is the beginning of everything. It is the reason we send rovers and spacecraft and radio signals into the dark. It is the reason we endure the cost, the frustration, the decades of waiting. It is the reason we keep reaching, even when we're not sure what our hands will find. But reaching and grasping are different things. Reaching is an act of curiosity, grasping is an act of possession, and the distinction between the two may matter more now than it ever has before, because the next thing we bring back from space might not be a rock. It might not be a mineral or an isotope or a crystal. It might be something that challenges the very definition of what it means to be alive. And if it is, we need to be ready. Not just with glove boxes and biosafety suits and containment protocols. Ready in a deeper sense. Ready to hold something unknown with respect rather than fear. Ready to ask questions before we demand answers. Ready to accept that the universe does not owe us safety, only wonder. And wonder, properly handled, is enough. Maybe your eyes have grown heavy by now. Maybe the world outside has gone quiet and the stars, if you can see them, are burning their ancient, patient light. That is all right. The passenger, if it exists at all, is not arriving tonight. It is still out there, somewhere, locked in rock on the floor of a dry riverbed, or drifting in the cold, dark ocean of a frozen moon, or sleeping in a form we do not yet have words for. And we are here, still curious, still cautious, still reaching. The next time you look up at the night sky, think about this. Every point of light you see is a sun. Many of those suns have worlds. Some of those worlds have water. And on at least one of them, on this one, water became life, and life became consciousness. And consciousness looked up and asked, "Is anyone else out there?" We do not know the answer yet, but we are closer than we have ever been. And the care we take in searching for it will say as much about us as whatever we find. There is a line from the Outer Space Treaty, written in 1967 by people who had barely begun to understand what they were reaching toward. It says that the exploration of outer space shall be carried out for the benefit and in the interests of all countries, and shall be the province of all mankind. Not all nations, all mankind. It is a rare moment in the history of international law where the language rises above the political and becomes something close to poetry. The province of all mankind. The sky belongs to everyone. And what comes back from it, whatever it is, will belong to everyone too. So perhaps it is not fear we should carry into this conversation. It is responsibility. The responsibility of being the first generation with the ability to reach another world and bring something back. The responsibility of being careful, not because we are afraid, but because we understand that some doors, once opened, cannot be closed, and the responsibility of remembering that the universe is not a thing to be conquered. It is a thing to be listened to, quietly, patiently, with the kind of attention we give to something we love. This has been a Streamberg Space Stories exploration. Thank you for being here. Thank you for listening. And if you drifted off somewhere along the way, that is perfectly fine. Sleep does not mean you missed the story. It means you have become part of it. Good night.
If you